ideas than I personally can. And yet again, sorry for all the people that have to sit in very congested spaces. Please forgive me. I'll make sure that the next lecture that we have, things will be better. So then, apart from that, I also wanted to point out that today's lecture we'll cut a bit short because as you can see, we were not very well prepared. So we'll keep it around 1 hour, and now we shall begin. So where was I? I was talking about the math students person. When I say math students, I simply mean the students who took PCM. I see the potential that a lot of you who think that they are bad at math or they cannot do math will end up doing way better than the people who actually took PCM. So, any of the math students here who understands any math student here who understands the notion of countable sets? Any of you who understand what makes a set countable? For example, if I ask you the question, wait, was anybody raising their hands? Yeah.
So a set with which a bijection can be formed with another countable set.
But then your definition already uses. But thank you so much for the try. What's your name again?
Augusta.
Augusta, thank you so much for your response. So for example, if I ask you that I would like to ask you, this is the sequence of natural numbers. Are they countable? Can I count natural numbers? With a show of hands, the people who say no, you cannot count natural numbers, please raise their hands. And those who say I can count the natural numbers, please raise their hand. Okay, so there are people who believe we cannot. It's like you're confused. Fine, I get it. So the point I'm trying to make is, if I began to count natural numbers, per se 1, 2, 3, 4, 5, 6, and so on, the people who said no are assuming that you cannot count them all. That's why they are supposed to be uncountable. But mathematicians are funny people, and I would like to tell you that natural numbers are actually countable. The way we have defined things, you can count natural numbers. And now people who are getting scared that, oh, this is going to be another series of lectures that we won't be able to understand and we'll need a help session for this help session. That does not happen to be true. The point is, all I'm trying to illustrate is that there are concepts that you think you understand, especially for the math students, that maybe you do not. And to be honest, most of mathematicians don't know what they're talking about. We just try to guess along things. And I use the word we because all of us are supposed to become mathematicians in one way or another. Whether you want to go into biology, astronomy, physics, chemistry, you're going to need a lot of mathematics. So also pay attention to your mathematics courses. I would like to introduce you to some of your seniors without whom this wouldn't have been possible. First and foremost, Varsit. He's the guy who has taken out an hour and an hour to record this lecture, so that all of you can access it even later, parts of it. Then we have got Varun, all of you know him from the group, that he has been a great help while planning everything. And then there's Rohan. Rohan, supposedly the network guy for me. I don't know how come he knows everybody in IISER Mohali. He's a great guy and he helps me out with everything. And then there are these two people, Aditya and Shivansh. Fantastic seniors, fun to be around. Don't be around them for too long. So yeah, these two are what keep me going, because a lot of times I wish to just give up and leave. And we have been planning to leave BSMS and learn to drive a train in IRCTC. We have been planning that. Let's see what happens. And then there's Vinayak. Vinayak is my tutor person. He's the guy who teaches me everything. So everything I know, he teaches me. So he's here just to overlook that I do not mess up. That's what. So Vinayak, if I write something that's supposedly wrong, please interrupt. So now, I would like to say a few things about mathematics. I know all of you must be thinking, "Bhai, बहुत ज़्यादा लंबा introduction हो रहा है." But I want you to be clear on these things. So there's a certain way mathematics works, right? So, for example, these are supposed to be straight lines, by the way. Are these two angles equal?
Yes.
Are you guys sure of it?
Yes.
And why are these two equal? Why are opposite angles supposed to be equal? Isn't this a question that's like saying that prove this is a triangle And you're like, you can just see it, these are supposed to be equal. What kind of a stupid question is this?
If two straight lines intersect each other, then it's a property that both opposite angles are equal. How you should show it? We can be read about the property. Prove it out like a straight line, 180 degrees. If we consider an angle, we can theta 1 and 1 and 2. Yes, we can.
You can prove it. And the point I'm trying to make is, and you said that we'll assume that the straight line has a total angle of 180, something along that, using something like that. But then the next question is, how do you know a straight line makes an angle of 180 degree? And like you guys said it, just look at it. But then we've got blind mathematicians as well, right? So the point I'm trying to make is, it's like saying that, okay, fine. The people good at English, I'm not at all good at English. What's a remote? Anybody could define a remote for me? One guy is, I need you to answer, is going to be an interactive session.
Remote literal meaning is distant.
An electronic device. What does electronic mean? What does something mean? The point I'm trying to make is that there are a few things, as much as we would want to remove all assumptions, there are a few things that we as humans know in our bones that we just take for granted. For example, if I ask you to define a point, what is a point? You would say something XYZ, but then the sentence you say, it would have certain words that yet again need to be defined. Because this is the paradox. Let's say you have an English dictionary. That looks more like a cube, but I want you all to believe that that's an English dictionary. English dictionary is composed of words, and every word in some sense is defined in the English dictionary itself. So it's all circular. What I'm trying to tell you is that you need something to begin with, like some of your friends pointed out, we need definitions. So we need definitions or axioms, and axioms, actually definitions and axioms are two different things. We need definitions and axioms to begin understanding things. And where do the axioms and definitions come from? They come from within ourselves, the things that we know for sure. As in, there are 5 people who are sitting together, they talk to each other, are you convinced of this fact? And they are like, fine, we are convinced of this fact. And then we try to reduce the number of axioms that we need. For example, all of the planar, the Euclidean geometry that you have read, such as vertically opposite angles are equal, a line makes 180 degree, and all of that, these can be deduced with the general axioms of mathematics that we have, along with 5 other axioms of geometry. One of them being I say this is theta 1, this is theta 2. So if a line intersects another line such that these two angles, theta 1 and theta 2, are not equal to 180 degree, we accept that these are parallel. And if a stupid person like me wants to ask you that why is this true, just say because we believe so. So fine. Now I told you how maths works. So we have definitions and axioms that we believe on, and then using the principles of logic and common sense, we derive everything else. Now, why, I don't know how many of you were part of a buffer group, but there was somebody on the buffer group that did not ultimately join IISER Mohali. But she posed a question. It is, why are polynomials defined the way they are? In the sense, why would mathematicians think such an expression should exist? Why did the mathematicians think so? Why should we care about such an expression? And the definition or the building block of mathematics that I gave you, that is, you start off with a few definitions and axioms and you build off a whole branch on it. But then I could set up a few definitions and axioms of flying elephants, but none of you would be interested in taking a course on it. So the point is, even though these ideas are abstract, and as a mathematician, you can define whatever you feel like defining, yet it needs to have some element of common sense some level of utility as well as some level of intellectual curiosity as well. So that's what I wanted to talk to you about. That is how mathematics works. As to answer this question, I can think that back in the days, there would have been a poor guy like me who, what's your name, sir?
Yash.
Yash. So Yash is supposedly a rich guy, and I am a poor guy. And Yash lended me 500 rupees. And then I gambled a little, and I had 200 left. So I gave Yash back 200 rupees. So then the question is, how much more do I need to pay Yash? Well, then you guys are smart. The point I'm trying to make is, I say that let me give back Yash X rupees. The infamous X returns. And then Yash claims that if you give me X money and you already gave me 200 rupees earlier, that should be equal to the 500 rupees I gave you. Thus, a linear equation is born. Similarly, we came across situations where we would need quadratic equations, which most of you would have dealt with in your mechanics classes, in your coachings and all. And thus, the mathematicians, being as crazy as they are, said that fine, if these such expressions as in sum a0 to x0, a1, x1, and so on are so important, it ends with an x to the power n, I'm just lazy. So if these expressions are so important, let us generalize them. Thus the polynomial was born. So now I've told you two things, that mathematics stands on axioms and definitions, and you're free to define anything, but then it should be interesting enough for other people to take a course on it as well. Fine. Now we shall begin with the task that have been assigned to you, that is beginning with calculus. The math students, are you learning something new, or is this boring? Well, if it is, you can speak up. There's no issue with it. I'll try to do better. So now we have talked about polynomials and everything, but we begin our study of the calculus with something called a set. And now I believe it is a chance for the math students to define a set for me. What is a set? Collection of distinct elements.
What is distinct is not required. Collection of elements.
A collection of elements. So you're saying that every set must have some element. So
A collection
of
anything.
yeah. Now that is the real definition. That is how crazy mathematicians get. So a set is defined to be a well-defined collection of objects. However, let me point it out that this is a naive definition, because mathematicians are even crazier than you and I can think. So, if any of you choose to consider mathematics major, in the third year you will actually learn the proper definition of what a set is. There are different, in fact there are all sorts of models, like you've read the atomic theory. So there's Thomson model, there's Rutherford model, there's Bohr model and whatnot model. I'm bad at chemistry. I got a C last semester, so I don't know. But the point is that in a similar manner, even sets are defined through different models. So there's an accepted model, and through that we work. And why is that? So I'll just leave you with a question, so that this is something interesting that you can go home and read on if you have the time. That is, there was a huge or a very great, I would say, mathematician, or a mathematics philosopher person, who defined a set. Like he said, it's a well-defined collection of objects. That is the definition we want to work with. He defined the set of all x's. The x appears again. We define a set of all x's. That is, I define a set which has all the x's such that x is not a part of S. So is x a part of S, or is it not a part of S? Because It's like I saw this meme a few days ago. I don't know how actually you guys are. That's Aditya Khurana for you, the guy standing here. And this is Shivan Dharmani for you, the guy standing at the back. And this is me. So he tells me that everything he says is a lie. And he tells me that everything he says is the truth. So who's lying and who's telling the truth? So you walk into such paradoxes with the naive definition of a set, and then a lot of you would want to say, why does it even matter? And to be honest, it does not. But we, like I said, we want to be very particular about things, because as you move on into this course, I will make you see things where if you're not particular about things, you'll make a mistake, and then you'll blame science and math that they do not work, but they actually do. You were not very particular about things. So I gave you a definition of set and at the same time told you that it does not work. Is it a chemistry class or what? But anyways, so we'll work with the definition that a set is a collection of well-defined objects. And when I say well-defined, so what's your name?
Shardab.
Dav. Okay. So Shardab, if I ask you who's your favorite cricketer, what would you say? And if I say who's the best batsman of all time, what would you say? So, as the best batsman, I write it best B because I am lazy, and heads are Guy Shah. So, he says it's Virat Kohli. What do you think? Who's the best batsman? Same. Okay. Vinayak says it's same. Defeats the purpose of me asking him. Who is the best batsman?
Sachin Tendulkar.
I like that, Sachin Tendulkar. So most of the class, I'd say 40% of the class is Sachin Tendulkar. So when I use the word well-defined, the point I'm trying to make is that we should all agree on it. As in, if I tell somebody that all of us, no matter where we are sitting on the planet, must write the exactly same set. But if I asked you to write a set with a single element, and the element should be the best batsman, we would all write very different sets. So in order for a set to be defined, according to our definition, which is wrong, there must be, the elements of the set must be well defined. There should be some sort of a rule, or there should be something which tells me that how do you write this set. That is, every person would agree that when I say A is equal to, or I don't know how many of you are familiar with it, but let's say I define a set of all natural numbers. This is a set. We'll work on the notations as well. So if I asked you to write a set which has all the natural numbers, all of us would write the same set. Do we agree on it? Yes. That means it is a set. Are we clear with the definition of a set? Okay. Now a few notations. It's going to be boring for the math students, but please forgive me. So the notation is such that there are two ways to write a set. First is the roster form. This is ROSTER, and there's a tabular form, and there's a set builder form. Mostly we use both of them, so we'll work with this. I don't even remember if this is supposed to be a form. Vinayak, is it? But yeah. So anyways, these two are the ones we're going to deal with, and if I've forgotten them, you can be well assured that then you don't need them, at least for the time being, because if we needed it, I would have remembered. So, roster form. What it means is that you're going to draw two curly brackets for some reason. I don't know why. And this one always is the words bracket. And you're going to list out all the elements in it. And when I say element, an element is defined to be the object that lies in the set. An element of set A is the object which lies in set A. So you write 1, 2, 3, and 4. That is your set. That's a set A. That's a well-defined set A. It has 4 elements. That is 1, 2, 3, 4. Now another way to write the same thing is, Yet again you draw the curly brackets. And you're going to give me a property, a rule, such that I can figure out all the elements of this set. And for that, usually, we use some predefined sets that all of us agree on. So if you remember, I wrote a set for you which was 1, 2, 3, 4, and so on. All the natural numbers. The set of all natural numbers is given by this weird symbol. You draw n, and then you give it a stick to stand on, though it is not using that to stand on. Then there's integers, that is, you come all the way. All of us are familiar with what integers are? So there are sets like these which we use to define our other sets. So I write that A is a set. This means, this is the equal sign, this means that A is a set. And I write X. X is a variable, it shows up again and again. So I would write that X, this means such that there's a colon, we want it to be more visible. You can also draw a vertical line. This means the set of all X such that this stands for belongs to, as in X lies in the set of all natural numbers. So A is the set of all X such that X belongs to natural number and X is less than 5. So this stands for less than, that is, this is, the crocodile opens his mouth and wants to eat 5, so this one's definitely smaller. So fine, these are how you write sets. Now a few things about sets that we'd like to discuss. I told you how to write a set, and for those of you who have not earlier studied set, I would like to give a small problem for you to solve. It's going to be an easy problem. I just want you to practice it. This is not integration symbol, this is curly bracket. X belongs to, X is such that X is to n. This is 6. Can somebody tell me the elements of this set? How many of you are studying sets for the first time? A show of hands, please. Okay, so I want all of you to answer this. Take some time. I've told you that n belongs to natural number. That means n can be 1, 2, 3, 4, 5. And that x is equals to 2n. So you need to enter 1, 2, 3, 4, 5 here. But I've also told you that x needs to be less than 6. So thus we began writing the roster form. You enter 1 here, you get x is equals to 2. It is less than 6. Fine. You enter 2 here, you get 4. 4 is less than 6, so you write 4. So all of you can follow up to this point, right? It's good. So now we have talked about sets. So it's not going to be a lot of use to you. But still, now that I'm teaching sets, I'll tell you a few more things about sets. There's something called a subset of a set. A subset of A what this stands for is a subset of B is a subset of A. And then I ask the question that what does it mean to be subset of another set? That is, I define B as the set of all sets A such that A has some X. No, sorry, why did I use A here? You already have mine. C has some X belonging to A. Or would this be an apt definition? It has some X belonging to A. Let me think about it for a moment. I could write it in a different way. Vinayak, what do you think? Okay. So I would define this as if small b belongs to B, then small b must belong to A. That is, if any element is a part of B, it must also be a part of A. In easier words, let us say this is a set A. So if I take any element from it and I write it down, it would be a subset. So one belongs to B and one belongs to A. So B is a subset of A. That means each and every element that belongs to B must belong to A. So you can write all sorts of subsets. You can take these single elements. A set with a single element is called a singleton element, a singleton set. So I can write B is a set which has 1. I can write another set which has the element 2. I can write another set which has the element 3. And then I can begin making pairs. So I can make an element which has 1, 2, a set which has 1, 2, a set which has 2, 3, and a set which has 1, 3. Those would be subsets as well. And then I can take the entire set that is 1, 2, and 3. That would be a subset as well. But that set would be A itself. Which brings me to an important property that every set is a subset of itself. Another thing that I would like, it is given as a property of the model. You know, I told you about the original definition of a set. So from the original definition of a set, we have something called phi. Phi is an empty set. It is a set which has no elements. So phi is an empty set. And yet again, with our definition, we have defined that phi is a subset of every set. That is, whenever you write any set, phi is a subset of that set, the set which has no elements.
The symbol between B and A, it is a C or it is less than?
Sorry?
What is the symbol between the two?
Oh, this is not an equal to sign. This is a U with a bar beneath. And then we'll walk on to the number of subsets, because we want to define it. And I understand this part is boring, but it's just for the sake of teaching your students about maths as well. You're going to be, yes?
I didn't understand the phi example.
Okay, fine. Phi. We'll deal with phi. Phi is called the empty set. So we said a set is a well-defined collection of objects, right? So I would define a set, I would define a collection which has nothing in it. That is well defined. If I tell you that I want you to think of a collection which has nothing in it, everybody would think of, in some sense, the same set. So empty set is a well-defined set. And then one must ask, why do we need it? Like I said, the definition that we are working with is an incomplete one. So the model that we actually use to understand sets, it needs, you remember I told you about the paradox that S is the set of all x's such that x does not belong to S. So that brings in the requirement to have an empty set. So like I said, we want to be very particular about things. Another thing that I want to leave you with is something called the operations of union and intersection. So I define a set A. It has some elements 1, 2, 3, and I define a set B which has the elements 1, 3, 5. When I say A union B, U stands for union. I define the set of all x such that x belongs to A or x belongs to B. So if an element is a part of A or B, it would be there in the set itself. Fine. So 1 is a part of it, 2 is a part of it, 3 is a part of it, and 5 is a part of it. Because it belongs to one of these sets. 4 is not a part of A union B. Or I must say, 4 does not belong to A union B because it does not belong to either A or B. Similarly, we have something called A intersection B, X such that X belongs to A and X belongs to B. That is, any element that belongs to both of these sets must lie in this set. That is, we have got 1, we have got 2, we have got 3, we have got 1, we have got 3, we have got 5. So I can see that 1 and 3 are common to both of these sets, right? How a set can be a subset of itself. The point is, yet again, it all relies on the definition. That is, we have defined what it means is that A, because no, it's not a part of B. A is a subset of B in the sense that any element that A has, it must be there in B. The opposite need not be true. For example, every element of A comes from B, right? But every element of B does not come from set A. So I would say that A is a subset of B.
But if A equal to B, then how it's a subset?
Okay. The point I'm trying to make is, fine, let us define A to be this. I stated that any element in A should be present in B. Is that true? So according to my definition, it's a subset. I know things might be a bit counterintuitive because you cannot understand where it's going to be used. But the reason why I'm teaching you this is because next semester you're going to have a course called Probability and Statistics. And yet again, a lot of people suffered because they did not know a lot on sets. So I'm not trying to teach you sets here, fine, you'll have to do that as well. What I'm trying to do is I'm trying to familiarize you with the idea of the sets. Like I said, most of you would be able to teach all of this better than me in the next semester. All I'm trying to do is introduce you to those ideas so that you could do it better than me. So A intersection B is the set of all x's such that x belongs to A and x belongs to B, which means I would like to change my set again. So 1, 2, 3 belong to A as well as belong to B. So this set would have the elements 1, 2 and 3, that is all. Now I would like to tell you something about the number of subsets, or I would say that these are two things that if you're interested you might take a look at it. These are not important. Okay, sure. So I say A is the set 1, 2 and B is the set 1, 2, 3. I say A intersection B. What does an intersection mean per se? Because like I said, definition, the words that we use them for a reason. So intersection means to meet, right? So when I say intersection, I mean that A intersection B should have elements that belong to A as well as belong to B. If you look at the set that I've defined here, that is A is equals to 1, 2 and B is equals to 1, 2, 3. A belongs to 1, 2, B also belongs to, 1, 2 belongs to A and 1, 2 belong to B. So therefore, 1, 2 belongs to A, or I should say A intersection B is equal to 1, 2. That is the set 1, 2. Right?
And we can also say that A is the subset of B.
Yeah, you can definitely say that. And the reason how equal sets can be subsets, I would like to clarify it. Because like I said, mathematicians try to be very particular. So if we define things, we define for a reason. I say that both of these are true. That is, A is a subset of B and B is a subset of A. That means, let me write this. So since A is a subset of B, every element in B should come from A, right? So I can take either of these elements, or I could even leave the set empty, because an empty set is the subset of all sets. We discussed that, right? However, I'm being told that B is the subset of A as well. That means fine. So, B, what I was trying to say, I wanted to start here. That is, B is the subset of A. So every element in B comes from A. But I may choose not to have any element in B, right? It would be an empty set, but like I said, an empty set is also the subset of all sets. However, this AND condition tells me that this is true as well. That is, A is a subset of B. So every element in A should come from B. So that means these elements should also belong to B, right? However, if I add any more element, let us say 5, so this would not work. Why won't it work? Is A still a subset of B? Yes, it is. All the elements of A come from B. However, the other statement would be violated. That is, B is no more a subset of A because B has an element that does not come from A. So A is a subset of B and B is a subset of A. Makes it mandatory that A is equals to B. So whenever you'll have to prove that two sets are equal, you'll prove that one is the subset of another and the other is the subset of the first one. Therefore, both of them must be equal. So because we need this property to work, and in terms of this property according to our definition works, thus, you asked the question, right? Your name, sir? Divyansh. Divyansh, right? So therefore, we need that every set that is equal is a subset of itself. There are two things I would have elaborated on as well, but this is not a course on set, and I believe that a lot of you are being bored as well. That when do we get to the fun stuff? So, those of you who are interested, yes?
You have said null set is a set of every subset, right?
Null set is a subset of every set, yes.
So how nothing can be equal to something like
How nothing can be?
like this set का कुछ value होगा 1 2 3 उसके बाद null set
Yes.
I'm saying that set must hold something, some object, right? 1 2 3 4, and null set doesn't hold something.
No, all I said is a set must be a well-defined collection. But then your collection can be empty, right? Like your wardrobe is supposed to be a collection of your clothes, but it can be empty if there's no clothes in your wardrobe. So thus we have an empty set. And to even give you a deeper answer for that, yet again you'll have to study the axiomatic definition of set theory. I'm not trying to touch this right now because that would be a bit advanced for you people. Although I believe that all of you can do it, it's too advanced for me. I would rather say that. So the point is, this does the same thing that 0 does. That is, when I talk about integers, right? When I talk about integers, 0 plays some role. 0 is the additive inverse. Or for anything, any set that we define which contains all the set of natural numbers, that is, per se, if we talk about integers, if we talk about rational numbers, we talk about real numbers, all of them have 0. So 0 plays an important role. That is, 0 is the additive inverse. You need it for something. For example, if I want x plus y is equals to x, there's no two natural numbers x, y that would satisfy this equation. If I write 1 plus something equals 1, you can give me no natural number which when added to 1 would give me 1. So you need a 0 for that reason. Like I said, that is exactly why I wasted a bit, or I would rather say invested a bit of your time in the beginning. That you can define anything, but we define things very particularly. We define things when we need them. For example, the natural numbers 1, 2, 3, 4, 5. We define the integers because I cannot subtract here. That is, you could subtract 3 minus 1, but you could not subtract 1 minus 3. So in order for subtraction to be defined on the natural numbers, you need integers. Then there are certain problems with integers, so you define rational numbers. Then there are certain problems with rational numbers, so you define irrational numbers. Are we clear on that? So that is what the empty set is for. If you want, you could talk to me in person, we'll talk about it. And I could tell you why it is the way it is, but then I would not recommend you to go very deep right now. We come to the next thing. I would now like to define something called the... No, I would rather ask you something else. I want you to see the use of it. How many of you are comfortable with this drawing? All of you. Somebody who is a little skeptical about what's being displayed here, please. Like, I do not want you to be shy. If there's some problem, if you have some trouble understanding it, please be honest. So I have drawn the graph. You guys call this a graph, right? I have drawn the graph. Y equals x squared. Fine. So what is it? I'm not asking this shit. It is a collection, a well-defined collection. Did you notice it? What is it? It's a collection of points, an infinite set of points. A graph is nothing, but it is a set of points. So what you're trying to write is, so this is what you're trying to write. For that is supposed to be an R. Yet again, something that it needs to stand on. This is the set of all real numbers. That is, B comes from the, or I would rather write this, something called for all. Right? What this means, this is an inverted A. It stands for all. What I'm saying is, no, this should not be. I would write it like this. So B belongs to real number. It is the set of all pairs of A and B. Such that B belongs to real number. And A belongs to real number, though B would work as well, because the square of a real number is supposed to be a real number. Though you would need to prove that in your third semester, you cannot just assume it. So B is equals to A squared. So this is the set that we are trying to get. So now we'll discuss that. But before that, I would like to ask you a question. What is a function? Any of the math students? Or I would like one of the bio students to answer it. What is a function? But even if you cannot understand a function, it's fine. Let's not talk about what is a function. Let's rather talk about, is this a function? If the bio students, is this a function?
Yes.
Yeah, that's what I'm coming to. Is this a function? Y is equals to x plus 1?
Yes.
Okay. So I believe all of you would have been told as function as something of a black box, almost like what happens in a factory. This is my F. F stands for a function. We discuss it. You enter an input from here, and you get an output from here, right? So that when I enter 1 here, I get 1 here, because 1 squared is 1. So that is what the function does. But is this a function? Well, similar to y is equals to x square, I can write an equation for it. We'll discuss the curves as well eventually, but I'll give you the equation for it right now. Don't be afraid if you cannot understand it, we'll discuss it in depth. Is it a function?
Yes, sir.
The bio students, is it a function?
Yes, sir.
It is a function, right? But that is where you are wrong, it is not a function. I'll tell you why it is. I hid a part of this machine This machine, like mathematicians, likes to be very particular. This machine says that if you give me an input, there must only exist one output. And when the same machine works here, it says that though you have the same input, you have got two outputs for it. So this is not a function. So I would like to build up to this definition using the definition of sets. That's all we needed sets for. I'm gonna give you what you're gonna need in sets. You're gonna have to not master, even I have not mastered, but you of course can. But you'll have to go through the procedure, or you'll have to become comfortable with the process of writing a set. You'll have to be comfortable with the process of a union, an intersection. Subsets, you won't need it that much. So using that, or you may need a subset, but the point I'm trying to make is I'll give you a few points. Set, and then there's the representation of sets, that is the set builder form and the roster form. And then there's union and intersection, that is operations, we call it operation on sets, is similar to plus and minus, or in some sense is similar to plus and minus. Union, intersection, and subsets. This is what you need to worry about. And De Morgan's law and all those are very natural laws, as in they are very intuitive, but intuitively this was supposed to be a function as well, but it is not. So we would not rely on our intuition, and if time permits, someday we will discuss the De Morgan laws as well. Fine. What's the time?
7.
7. When did we start? 6. Okay. So I would like all of you to take a break, seeing that all of you are exhausted. Let's take a 5 to 10 minutes break, and we'll continue for another half an hour per se, and we'll leave. A 10 minutes break. What's the time right now? 7 to that. I have 1, 2, 3, 4, 5. So I can count them in some sense. Right? Is it that if I give you an element, can you in some sense tell me the next element, or can you write out each and every of its element if I told you to? That is the problem that we are dealing with. It is along those lines. So we define something called cardinality of a set. And I don't want you to make note, this is irrelevant to you. If you choose maths pre-major, you'll be studying it in your 3rd semester. All I'm trying to do is expose you to a new idea. So cardinality means the number of elements in a set loosely, incorrect definition, but you can understand it that way. So if a set has 3 elements, I would say its cardinality is 3. If a set has 4 elements, I would say its cardinality is 4. But then cardinalities could be equal. There's something called a bijection, which we'll be discussing in the next class. That is exactly why I'm telling you this, so you will look forward to the next class. That our friend Agastya also mentioned. That is, if 2 sets can have a bijection between them, there's something called, there are special types of functions. There are 3 types of functions, special functions, which are called injective function, surjective function, bijective function. Fine. So if I can draw a bijection between 2 sets, because come to think about it, what is your function? Let me think of a nice function. This is a function, and like I said, it is a set of ordered pairs, a set of points, a set of couples per se. That is what a function is supposed to be, with some special conditions of course. But the point I'm trying to make is, it is a relation. In some sense, the couples come from 2 different sets. Your x comes from this set and your y comes from this set. Right? So in the sense that when I write A comes from a certain set, B comes from a certain set. Here both of them are equal. That is, A comes from the real numbers, this is the real number line, this is the real number line. But that is not necessarily true. I could define a function for natural numbers as well. It is not necessary that all functions must look like this. That is, it need not be defined on all real numbers. Yes?
That is a function.
Yeah, this is a function.
What's the output of it?
What is the output of this? Oh, well, not every function needs to be written as an equation, but I'll write this way. This is what I was trying to draw. So it's not looking like it, of course. But
The function is the equation we are working.
yeah. Like I said, a function is a set of points. And when I talked about set builder form, I told you that you need to give me a rule so that I could write out each element in the set. So therefore, this here, this is not ex, this is e raised to x. This here is the rule that is going to help me determine this function, the set of all points in this function. But where was I? Yeah. So I was talking about functions. So the point I'm trying to make is at the end of the day, it is a set of points, right? We are taking two sets and we are defining a relation between them. We are defining couples for them, right? So when we define such functions, we can define special types of relation. One such relation is called a bijection or bijective function. And if I take two sets A and B, and I can define a bijection between them, that would mean that it is a, what do you call it? That their cardinality is the same. I'm not saying that there needs to be a particular function, as in if I take two sets, the set of all natural numbers and the set of all integers. If I can couple elements of these together such that they fulfill the criteria of the bijective function, I will say the cardinality of this is same. Mind you, I am not saying that every function that you define from this set to this set, because like I said, functions are defined between two sets. So every function that you define between these two sets, they need not to be a bijection. But if you can give me even a single bijective function between the two sets, then what you have are two sets whose cardinality is the same. And therefore, cardinality is not the number of elements in a set, because these two sets, they are not equal. And this wouldn't be a suitable definition, but what I'm trying to say is that natural numbers come from integers. Every natural number is an integer, but it's not vice versa. So if I was to think of using the notion of numbers, I would say that fine, if this is your n, every element here is here, but every element here is not here, which in some sense tells me that this should have more number of elements. But then when we talk about sets which are infinite, that is, they do not have a finite number of elements, the notion of number of elements in a set falls weak. It is not a very well defined function, though as mathematicians, like I said, they are very crazy people. We have defined some words for these numbers, but they are not necessarily, all I'm trying to say is that cardinality, the word cardinality, means the number of elements in a set only for finite sets. And if you can draw a bijection, if you can define a bijective function, which we'll talk about in the next lecture, between two sets, then that would mean that the sets have the same cardinality. So that is what we will be discussing today. That is it. But I would have started functions, but the point is that that would have taken me another half an hour. I do not want that for you guys today, especially given that some of your peers are relying on lectures. The next class, we will discuss something called relations. We will discuss something called functions, and we will discuss something called trigonometry. Now, in the end, I want to leave you with a question that I want you to think of on your own. I do not want you all to use ChatGPT. How many of you are aware of this? Now, the question I'm trying to propose is this formula applicable when x is in degrees, radians, or is it applicable in both the cases? Radians. Sorry, somebody else said something else. Somebody said both. Why is it only applicable in radians?
We define trigonometric ratios for radians.
No, but you could convert the radians into degrees always. For example, let us think about it this way. Okay, fine. You wanted to say something.
Like, we use the angle only in radian when it's standalone, like not associated with something, right?
Okay, fine. Then just tell me something. Am I writing something wrong? This means evaluated at. That means first we're going to evaluate it, and then we're going to put in the value x equals to pi by 4. In case you people do not know, pi by 4 in radians is equals to 45 degree, and we'll even talk about the angle conversion, but I believe most of you would know it already. So is this formula alright? It is wrong. It's right. Is it right or is it wrong? A show of hands for the right ones. And a show of hands for the wrong ones. And a show of hands is, please leave me, we are too bored for this thing now. So, what I'm trying to make is, this is correct. And we'll discuss why this is correct. For those of you who think that there's something wrong with it, do not understand it, it's fine. Like I said, it's my responsibility to make you all understand this. But, is it still right? Why? But I just said that pi by 4 in radians is 45 degree. You agree with this, right? So then why can't I replace pi by 4 with 45 degree? Yes?
Probably by the expansions we do like integrals for like x square or
I've got people who are smarter than me. Right? But what I'm trying to say is, this is still correct. Now I need you to find the reason why this is supposedly a sine function even if it does not look like one. That is my best attempt at drawing a sine function. Now I need you to find me an answer to the question that why do all the textbook in big bold letters write that this is only applicable for radians when I told you right now that this is also applicable for degrees. And with that I end your first lecture. Thank you very much all for coming here. I'm really sorry for the logistical issues, and because I was stuck with the logistical issues, the lecture could have been better planned, it could have been more entertaining. In fact, I had even planned demonstrations for you, but then on the last moment I was asked to rather teach you something else than what I was planning for. So I hope to see you all and your friends and more people in the next lecture. I hope all of you enjoyed it, and I will put up a poll on a Google form asking you about your review of the lecture, whether you understood something or not, would you like something else to be a part of this lecture, or anything like that. So I request all of you to please fill that Google form. My name is Amir Ashraf, and thank you very much.